students, myself Dr. S.S. Naik from KK1 College of Engineering will be dealing with today on unit number 6 Cayley-Hamilton theorem and its sum of the properties. So I will start with the Cayley-Hamilton theorem. This theorem states that every non-zero square submatrix satisfies its own characteristic equation. That is, if the statement of the theorem, every square matrix satisfies its own characteristic equation. Students, already you have studied the characteristic equation of a square matrix. So, if A is a 3 by 3 matrix, then its characteristic equation is given by the characteristic equation of A is determinant of A minus lambda I is equal to 0. A minus lambda I is equal to 0. Now you can write this equation. When I expand this equation, its expansion gives, that is what we call, this is lambda cube minus s1 lambda square plus s2 lambda minus determinant of A is equal to 0. Now here in this equation, what is the S1, S2 and S3? So we will state that S1 is equal to sum of diagonal elements of A. Diagonal elements of A. S2 is equal to sum of minus of diagonal elements of A, and then this is the determinant. This is determinant of A is the determinant of A. So if A is a 3 by 3 matrix, then its characteristic equation is given by determinant of A minus lambda I is equal to 0. That is, its equation is lambda cube minus s1 lambda square plus s2 lambda minus determinant of A is equal to 0, where s1 is equal to sum of the diagonal elements of A, s2 is equal to sum of minus of diagonal elements of A, and determinant of A is the determinant of A. So, according to this Cayley-Hamilton theorem, it states that every square matrix satisfies its own characteristic equation. That means this lambda is replaced by A. So, I will write in that form, that is the Cayley-Hamilton theorem in the form of that equation is given in the form of, say for example, this equation becomes, this is A cube minus s1 a square plus s2 a minus determinant of A is equal to 0. Minus determinant of A is equal to 0. So this equation is now satisfied by the Cayley-Hamilton theorem. Now say for example, we take an example becomes clear to get the idea. So what we do is, I will take a 3 by 3 matrix. Say for example, suppose A is a 3 by 3 matrix. 3 by 3 matrix. Then its characteristic equation is, say for example, I write that is equal to lambda cube minus 3 lambda square plus 2 lambda, then minus 6 is equal to 0. So I have taken a 3 by 3 matrix. Its characteristic equation is given by lambda cube minus 3 lambda square plus 2 lambda minus 6 is equal to 0. Then according to the Cayley-Hamilton theorem, this equation has to become, this is a cube minus 3a square plus 2a minus 6i is equal to 0. Now if you see this equation, that a cube minus 3a square plus 2a minus 6i is equal to 0, this is what we call the characteristic equation satisfied by the given matrix A. Then if I call this is equation number 1, then what is the use of this Cayley-Hamilton theorem? Now the Cayley-Hamilton theorem can be used to find A inverse, that is pre-multiplied by A inverse, then we get A inverse A cube minus 3A inverse A square plus 2 A inverse into A minus 6 A inverse into I is equal to 0. So one of the A inverse from this A cube will get cancelled. That implies this becomes, this is A square minus 3A, then this is plus 2I, that is A inverse into A is an identity matrix, that only we have seen, and then this is minus 6 A inverse is equal to O. Now this is a null matrix on the right hand side. So from this you can see that this implies that 6A inverse is equal to 6A inverse is equal to A square minus 3A plus 2I. This implies that A inverse is equal to 1/6 of A square minus 3A plus 2I. Now this is equation number 2. Now this equation number 2 is used to find A inverse of the given matrix by using the characteristic equation of the given matrix A. So we will take an example to clear this idea and then we can go to the next part. So this is one use of the Cayley-Hamilton theorem. So we will take an example and we will make it clear from find the characteristic equation of matrix. The question is, this is an example, find the characteristic equation of the matrix A is equal to 1, 2, minus 2, 1, 1, 1, 1, 3 minus 1. This is a 3 by 3 matrix, and hence find A inverse. Hence find A inverse. Now, when this occurs in the examination, this will carry 6 marks in the examination for finding A inverse by using Cayley-Hamilton theorem. Okay. Now, here the question is, find the characteristic equation of the matrix, and then you are finding A inverse. That means indirectly you are using what we call the Cayley-Hamilton theorem, because you have other methods to find A inverse also. What are the other method? A inverse is equal to adjoint of A divided by determinant of A. So that method also you can use to find the inverse of this. But he has asked you to find A inverse by making this of its characteristic equation. So therefore you have to use the Cayley-Hamilton theorem to find the inverse of this. Okay. So we'll go to the solution of this. So first let us find the characteristic equation of A. It is given by determinant of A minus lambda I is equal to 0. So A minus lambda is equal to 0 is actually equal to, now I write on this side, this implies this is the determinant of 1 minus lambda 2 minus 2 1 minus lambda 1, then 1 3 minus 1 minus lambda, the determinant of this is equal to 0. So this is the characteristic equation of the given matrix A. So when we expand this equation, that is, when I expand this equation, I'll be having, this is given by, this is the lambda cube minus S1 lambda square plus S2 lambda minus determinant of A is equal to 0. So we'll find S1. What is S1? S1 is equal to the sum of the diagonal elements of A. That is the given matrix. 1 plus 1, then you are having minus 1. That is 1 plus 1 minus 1. 1 plus 1 minus 1 is equal to 1. That is S1. Then what is S2? S2 is equal to the minors of the diagonal elements. The minors of the diagonal elements of A. That is given by, that is the determinant of the diagonal element 1 is 1 1 3 minus 1 1 1, and then you are having 3 minus 1, that is the minor of the first element. That is, delete this row, delete this column, 1 1 3 and this minus 1. Okay. Then you have plus the minor of the second element, the minor of this element, delete this and delete this, that is equal to 1 minus 2, 1 minus 2, and then 1 minus 1, 1 minus 1, and then the third element is 1 minus 2, 1 minus 1, then we have the third minor is what? The minor of the third element, that is delete this and delete this, 1 2 1 1, 1 2 1 1. Then when you expand this equation, now this is equivalent. This is minus 1, this is minus 3. Okay? Then this is plus, this is minus 1, this is plus 2. And this is plus, you are having, this is 1 and this is minus 2. So, if you take the sum of all this, is equivalent to, this is minus 4, and then you are having, this is minus 4, 1 is minus 5, minus 7, and plus 3 is equal to minus 4. Then, when I find the equation, the determinant of A, what is the determinant of A? Determinant of A is also equal to minus 4. Let us find determinant of A. What is determinant of A? The determinant of A is given by, when I expand the given determinant, then the determinant of A is minus 4. Okay, so we'll put that S1 is equal to 1, S2 is equal to minus 4, determinant of A is equal to minus 4. I'll substitute these values in this equation. Now, say for example, this is my equation number 1. In that equation, if I put this value, I'll have it, that is lambda cube minus, what is S1? S1 is equal to 1, that is lambda square. What is S2? S2 is equal to, you are having, S2 is equal to minus 4. So, minus 4 lambda, that is equal to minus 4 lambda. Okay, what is the determinant? Determinant is minus 4, minus of minus. So, this becomes plus 4 is equal to 0. Okay, so that implies that lambda cube minus lambda square minus 4 lambda plus 4 is equal to 0 is the characteristic equation of the given matrix. Now, from this given matrix, we will have to apply the Cayley-Hamilton theorem. That means I am having replacing lambda by A by Cayley-Hamilton theorem, by I write CH theorem, means Cayley-Hamilton theorem. So what you get? This becomes A cube minus, this is A square minus 4A plus 4I is equal to 0. Now this is equation number 2. This equation number 2 is by using Cayley-Hamilton theorem. Then we want to find A inverse from this Cayley-Hamilton theorem. Okay, so how to find? Pre-multiply by A inverse. Pre-multiply by A inverse. What do you get? This is A inverse A cube minus A inverse A square minus 4 A into A inverse plus 4 A inverse into I is equal to 0. So, when you pre-multiply the given matrix by A inverse, you got A inverse A cube minus A inverse A square minus 4A inverse plus 4A inverse I is equal to 0. So, when you are multiplying A cube by A inverse, one of the A will get cancelled from this. So, that means I am going to get in the form of this equation, one of the A will get cancelled. You get this is A square from this, then one A will get cancelled minus A from this, then A into A inverse is equal to I becomes equal to minus 4I. Okay, and you have plus 4A inverse plus 4A inverse, because A inverse into I is equal to A inverse, and this is equal to 0. Then from this you want to find A inverse. So you will get, this implies, I write in the form of that 4A inverse is equal to, this will go on that side, becomes equal to minus A square plus A minus becomes plus 4I. So this implies this implies A inverse is equal to 1/4 of, this is 1/4 of minus A square plus A plus 4I. Okay, now this is the formula to find A inverse of the given matrix by using Cayley-Hamilton theorem. Now what we do, we find A square. A is already given to you, and then 4 times the identity matrix. We will substitute that values in this equation, and we are going to get A inverse by using Cayley-Hamilton theorem. So therefore, what we will do? So A is known to you. So you have A square is equal to. So I will write that to find A square. A square is equal to, this is A into A is equal to, what is A? A is equal to, you will be having 1 2 minus 2 1 1 1, then 1 3 minus 1. Then similarly, so when you multiply this value again, you get this equal to 1 2 minus 2 1 1 1 1 3 minus 1. So you get this is A square. Now how to multiply? This is row by column. Multiply the first row by first column, you will get the first element, and this value is given by, and write the value directly. First row by first column, first element. First row by the second column, second element. First row by the third column, the third element. And that 3 elements I'll write directly 1 minus 2, 1 minus 2, 2, and then you are having 3 6 minus 2. I'll be having that 3 2 2. Now this equation is A square is known to you, then A is the given value, but we want to find minus A square. So therefore each of the elements will be minus values. Minus A square is equal to, what will be that? This becomes minus. So minus A square is minus 1, then plus 2 minus 2, and then minus 3 minus 6 plus 2, and then minus 3 minus 2 and minus 2. This is what? This is minus A square. Minus A square is known to you now. That means I want to find minus A square plus A and plus 4I. Okay. Now what is 4I? 4I is equal to 4 0 0 0 4 0 0 0 4. How you get this value? Because I3 is equal to 1 0 0 0 1 0 and then 0 0 1. Then that is multiplied by 4. Therefore it has become 4 0 0 0 4 0 0 0 4. So therefore all the values are known. Minus A square is known, A is known, 4I is known. So you can substitute these 3 values in this equation number 3. Then you get what we call A inverse, and that A inverse is given by, A inverse is given by, A inverse is equal to, this is 1/4 of this matrix, that is minus A square is minus 1, 2, minus 2, minus 3, minus 6, 2, then minus 3, minus 2 and minus 2. Okay. Now this is what we call minus A square. This is inside here. Then plus A. I'll have this is plus you will have it 1, 2, minus 2. That is 1, 2, minus 2. 1, 1, 1. 1, 3, minus 1. 1, 3, minus 1. And then you are having plus 4i. You will be having plus 4i. I write in this side. This is plus. You are having determinant 4, 0, 0, 0, 4, 0, 0, 0, 4. Now, just try to understand. You are adding 3 matrices. When the 3 matrices are added, you have to add the corresponding elements of the 3 matrices. That means you will have to add the corresponding 3 values. So, you will have to add the 3 elements minus 1 plus 1 and then you are having plus 4. Minus 1 plus 2 will get cancelled. The first element will be 4. So, I will write that value is in the form of, that is 1 by 4, 1 by 4, and then when you add the corresponding elements, so that is equal to 4. Again, the next element also becomes 4. The third also element becomes minus 4. And then minus 2, minus 1, minus 2, minus 1, 3, and then minus 2, 1, 1, minus 2, 1, 1. Okay. Now therefore, this is A inverse. A inverse of the given matrix by using Cayley-Hamilton theorem is given by this result. Is it clear? Now just try to understand what we did. So we have stated the Cayley-Hamilton theorem, that is every square matrix satisfies its own characteristic equation. Then by using that characteristic equation formula for a 3 by 3 matrix, when you are having that lambda cube minus s1 lambda square plus s2 lambda minus lambda p equal to 0. By using that, I made use of that equation to find A inverse. And by using that method, I got A inverse is equal to 1 by 4 and now this value. Okay. Thank you very much. In the next video, I will move for the next part of this type of questions. Thank you.